Okay. Does that? Yeah. Okay. So, good morning. I fully understand that I'm the last hurdle between you and a nice, hopefully sunny afternoon in Florence um, or at the airport. And so I'll try to stay brief and to stay on time. So in the last classes, what we've seen mostly on Wednesday is how to include a Coulomb interaction in the problem, and how to account to open channels using the optical potential, so the optical model. And we've also seen how to that you need really to include the breakup channel to correctly reproduce the elastic scattering of halo nuclei, so of loosely bound system. And yesterday we've seen how to solve that three-body problem. We've seen the CDCC method, so the Coulomb discretized coupled channel method. Mentioned the time-dependent approach in which you simulate the projectile target relative motion by a classical trajectory, which makes everything much simpler. And we've also seen the Iconard approximation. And we've seen a comparison between the three technique on the particular case of the Coulomb breakup of carbon-15. And so we've seen the weaknesses and the advantages of each of these methods. What I would like to do today is to discuss exactly what we are sensitive to. So how does the reaction proceeds first? So look at the dynamics of the reaction, and then look at what it is sensitive to what it is sensitive, and what you can actually infer from these reactions. So the plan of the class is the following. First, we'll look at the dynamics of the reaction, and then look at the what we are sensitive to, and then I will make a short summary of that, followed by a discussion using another method to describe the nucleus in order to have a clearer link between reaction and between reaction and structure. So this is a slide I've showed yesterday. So this is a calculation performed by Henning and Spencer using the time-dependent approach. And the difference between left and right, so the data are the same. They are the data from Nakamura of 2009. And the difference between the left and the right-hand side is that the left is a dynamic calculation and the right is a first-order perturbation theory, assuming a purely E1 transition. So you start from the ground state, you have E1 transition to the P wave continuum, and you stay there. There is no dynamics. And so what we've seen, and the important is here. So what you should look at is the black dotted line, because that's the output of the calculation. There is no folding with the energy resolution, and there is no scaling to the data. And the important thing is to look at these two curves here, the maximum, and we see that there is a significant difference between the two. And the difference is really significant. It's about 20% of the cross section. And so something's wrong. And so the question is why? What's not going on with this simple picture that you have? The projectile arrives, it interacts with the target. You have this tidal force that I've mentioned. It's mostly an E1 transition, so dipole excitation. You go from the S bound state to the P continuum, and then the two particle separates from each other, and they stay in that in that problem. And it's something we've looked at in more detail with Daniel Bay in 2005. And so here is, we've looked at different impact parameters. This is within the time-dependent framework, so the semi-classical approximation. And we've looked at this breakup probability partial wave per partial wave. So we've looked at particular trajectory. So we've not looked at the whole we've looked at the whole cross section, but we first focus on a partial wave trajectory per trajectory, so impact parameter per impact parameter, and we've looked at different velocities. So a quarter of the speed of light, about 0.30% of the speed of light, and about a third of the speed of light. And the different color corresponds to different impact parameters. So we start the red light, the red line is 40 Fermi, then the green one is 60, then you have 80, and then you have 100. It's the black line. So 100 Fermi, it means that the projectile and the nucleus pass by 100 Fermi from each other. So you're really far away. And so at these distances and at these velocity, you would assume that the first order of the perturbation theory works well. You're far away, it's a distant field, the velocity is high enough, but we see a distortion. And it's a distortion which is not small, it's more than 10%, so nearly 15% here. And it gets better when you go higher and higher in velocity, but even at the third of the speed of light, you still have some distortion here, and we need to understand what's going on. So this is a work that we did in 2005, but others have done that. So Stefan Tüpel and Gerhard Bauer did in 2001. Then S. Benson, I've mentioned before, Birch and Snover looked at about the same time for a different system. And so what we did is, okay, let's look at the partial wave analysis. Let's look at what's going on. And the black line, this is at what one calculation, 100 Fermi, so we place ourselves at a distant field. And this is the total. So the black line is the total, and then you have the P wave, you have a D wave, and you have an S wave. So, and this looked strange. So not only it's the P wave is dominant. So you start from an S wave, you have an E1 transition, you go mostly in the P wave in the continuum. So that's fine, but it's not the only one. There is no nuclear interaction here. So it's purely Coulomb interaction. And we see a significant contribution of the D wave and on the S wave. And that can only be explained if you have a quadrupole excitation for the D wave, but for the S wave, you're stuck. So there is no way you can really understand what's going on. The only way you can explain that is if there are higher order effects. So what we did is look at the wave function and this breakup probability evolving with time. So we have this semi-classical vision, and this is what is shown here. So this is this breakup probability as a function of time. So the time 0 is a time of closest approach between the projectile and the target. And so what you see is that, and this is the distance between them as a function. This is the distance, the corresponding distance. And so when they are far away from each other, so about 1000 Fermi, nothing happens. So up to there, that's fine. And then when they come close to each other, at about 100 Fermi, something happens, and the breakup probability starts to increase dramatically. And initially, everything is in the P wave. So it's the blue line that you see here. It's there. Then you have oscillation. These are quantal effects. Fine. And then we are at 1000 Fermi. You could say that's far enough. So nothing happens. But we see that the P waves start to be depleted. So you have a decrease in the P wave. The total cross section, the total breakup probability, which is here, the black line here, stays constant. But there is a depletion. So the P wave, starting from the value of the total breakup probability, start to be depleted and decrease. And at exactly the same time, the D waves start to increase. And so what we understood that in the following way. So if we look at, if I do something similar to what Jeff Tostervin did, so I look at the spectrum of the nucleus, and that I plot as a function of the orbital angular momentum. So this would be initially, so I will divide it into different partial waves. So I have the S wave, the P wave, and then the D wave here, and then other waves, of course. And I start from the loosely bound state here. So you have the loosely bound state in the S wave. And what happens is mostly you have, and initially you have it's not what I want to do. Initially, what you have is a dominant E1 transition from the ground state to the P continuum. It's just an electromagnetic transition. You start from an S wave, you go in the P wave in the continuum. And once you're there, what happens is E1 is a long-range interaction. It's the dominant part of the Coulomb. It's the longest range of the Coulomb interaction. And what happens is that that P wave is that you have another E1 transition that couples and that moves through couplings in the continuum, and that deplete the P wave, the initial P wave, towards toward the S and D continuum, and that explains what happens here. So what happens is you have initially a very strong E1 field, dominant dipole field, that breaks the system from the P wave from the S wave to the P wave in the continuum. And then there you have this higher order effect. If you remember the plot by Jeff Tostervin, where you had these arrows a bit everywhere and showing that you had different contributions, it's exactly what's going on here, but we see it evolving with time in this semi-classical vision of the reaction. And you first go to the P wave, and then the P wave is depleted towards the S and the D wave. And that's why the total breakup probability doesn't change, but you have an evolution. And that affects different breakup observables, as we've seen in the calculation of Henning. So taking the first order approximation gives you a rough idea of what's going on. It gives a good first order estimate of the breakup cross section, so that's fine. But it's not the full picture, so you have higher order effects and you have to take them into account. And these play even bigger role when you also have E2 transitions that can interfere, significant E2 transition that can interfere with these second order E1 transitions. So I won't go into the detail, but that means that you need really to pay attention when you use just first order perturbation theory. It gives a rough idea, it gives a good first estimate of the reaction process, but it's not the full picture, and you should pay attention to that. Now, another input that you have, so first it's the whole reaction mechanism, but one of the inputs that is significant, that has also a significant influence in nuclear reactions, is the choice of optical potential. So this is a calculation we did with Gerald Goldstein and Daniel Bay for the nuclear breakup of beryllium-11 on carbon 12. And this is the breakup cross-section, once again, as a function of the energy between the beryllium-10 core and the neutron after dissociation. And so we have this bump, which is due to the resonance. I'll come back to that in a minute. But we perform 4 different calculations. We use 4 different optical combination of optical potential. So 2 for the beryllium-10 core and the carbon target. The one is from Jim Al-Khalili from University of Surrey, Jeff Tostervin and Brooke, who was probably a student at the time. So they develop an optical potential to fit existing data for beryllium-10 elastic scattering on carbon 12. So this is rather reliable. And then another one that we found in the literature in the PIERRE and PIERRE compilation I've mentioned before. And we used it just to see how the cross section can change. And then for the neutron target, so the neutron carbon 12, we use two different potentials, Beckettian Green-Lees as usual, and Comfort and CARP for another existing potential. And what we see is we're not that much sensitive to the neutron carbon potential, but the difference that we see here, which is nearly a factor of 2 in the calculation, is due to the barium-10 core, the barium-10 carbon interaction. And so you have a very significant influence. So you need to take that into account and to know that sensitivity. So it's very important to know that. Now this is a bit of cheating because it's a nuclear dominated process. So I'm looking at something which we know is significant. But other people have also looked at the sensitivity to that interaction in Coulomb breakup, because in Coulomb breakup, you could say Coulomb is dominant. So what's going to happen? And here is a calculation by Tupel and Shyam for the breakup of carbon-19. And what you see here, they did a fully dynamical calculation for the Coulomb breakup. So these are the two lines here. So you have the solid line, which is Coulomb plus nuclear, and when they did a calculation with only the Coulomb interaction, they got the dashed line. And so at very low energy, so for less than 0.3 MeV, there is no clear, very significant influence. But at larger angles, at larger energies, it's more significant. And if you dig into a little bit more into the process, you can see that also it's mostly at large angles. So when the two nuclei, when the center of mass of the carbon-18 neutron is deflected at larger angles, the nuclear interaction has a larger effect. This makes sense, okay? Larger angles correspond to shorter distances. So the core and the neutron come closer to the lead the lead target, and they are deflected at larger angles. So these are the two things that I wanted to emphasize on the reaction mechanism. High order effects are important, so you need to take them into account, and you need to pay attention to the sensitivity of the calculation to the optical potential that you put in your model. Now I would like to look at a little bit more at what we are sensitive in these reaction, and to put a few things straight. So the first thing is I go back to this calculation by Tupel and Shyam for the carbon-19 breakup on lead, and they perform the binding energy of the neutron, the valence neutron in carbon-19 is still not well known experimentally. And so they performed two sets of calculation, one with a binding energy of about 500 keV, and one where they are slightly more bound, and you see that there is a clear difference between the two calculations. And so this favors this binding energy. So your breakup calculation, and this is very important, is highly sensitive to that binding energy. So you could get some information about the binding energy by looking at the breakup cross section. Now, apart from the binding energy, everything I've said is using a very simple single particle description of the nucleus, okay? We use an effective description of the nucleus, assuming you have a core in its ground state, and then a neutron that is loosely bound to the system, and you describe that using an effective potential. And in particular, the wave here, the wave function is normalized to 1. It's normalized to unity. And what usually people say that this is just, of course, an approximation. You have an admixture of configuration. You have more than just one configuration. You have actually a set of configuration. The core can be in its excited state, and the neutron can be bound to that. And so it's a much more complicated system. And so what the people have said is that, and these overlap wave function here are normalized to something which is lower than 1. And this is what we call the norm of that wave function, is of overlap wave function, is what we call the spectroscopic factor. And so Gregor Hansen and Jeff Tostevin started to say, okay, but that means that we make an approximation. We assume that the norm is 1, but actually the norm is not 1. So when we compare, what we can do is compare the calculation to the data, and the difference, the calculation are higher than the data, so we can scale down to the data and get this spectroscopic factor. So you assume that the single particle wave function is fine. It's just an approximation, and the norm, there is a difference in the norm. And so the goal is to say, I measure this, I compute this. So Gregor measures the experimental cross-section. Jeff computes the theoretical breakup cross-section, and you do the ratio of the two, and you get the spectroscopic factor. Okay, makes sense. The question is, does it? Are you really sensitive to the whole norm of the wave function? You need to be sensitive to the whole range of the wave function in order for that to be true. And one of the questions that arose and that we ask ourselves with Filomena Nunes is, isn't breakup peripheral? Aren't you just probing the tail of the wave function? So your wave function decays is slowly decaying. It has a tail, and it slowly decays with the radius. Okay, depending on with this kappa directly related to the one neutron separation energy. So it's, since we have a loosely bound system, kappa will be small. This will decay very slowly. So about 50% of the wave function will be basically in that tail. The question is, aren't you just sensitive to the tail? And so aren't you just measuring the asymptotic normalization coefficient? So this coefficient here that gives the normalization of the wave function at large distances. That's a question. How do you do that? So what you need to have is wave functions that are identical in the asymptotics and very different in the interior. Okay, that's the best way. You perform two calculations, and if there is a change, it means that you probe the short distances. If there is no change, that means that you are only sensitive to the tail. So one possibility, and it's something that is a bit, it's like killing a fly with a bazooka. Okay, it's a very complicated mathematical tool, and we use supersymmetric transformation. This is something that Daniel Bay has developed in quantum physics in general, and so what we need is two potentials that lead to exactly the same asymptotic but very different wave function in the interior. And so to do that, what we did is we started with this is the effective potential. So it means it includes the centrifugal barrier. And I think for this one, it's the case we did for boron 8, but the principle is the same. You start with a deep potential. Fine. And the deep potential is because you have a loosely bound state, but you also have a deeply bound state. Okay, this is an unphysical state. You don't care about the state. What happens? You have a deeply bound state. It means that you have a node in your wave function. Okay, the radial wave function has a node. This is the physical wave function, so the wave function for that loosely bound state. But because there is a deeply bound state in the same partial wave, it means that there must be a node in the wave function that we care. And the reason for that is that the two have to be orthogonal to each other, so they have to cancel when you project one on the other. Okay, so this is the one obtained with the deep potential. And now the magic is you use Daniel's tool. And you remove that state. So there is a supersymmetric transformation that gives you a potential that removes the state, but keeps exactly the same asymptotics. So what you see here is you go from a deeply bound potential to the supersymmetric partner, which is a shallow potential. It still has this loosely bound state at exactly the same energy. And because the potential has the same tail, the wave function has exactly the same behavior. But you remove the node because you remove the loosely bound state. So your wave function now has a usual behavior. And so it means that we have wave functions that are strongly different within 3 Fermi, so short distances, very different, but exactly the same tail. And it's not exactly that we fit the ANC to be about the same. They are identical. It's exactly the same value. Mathematically, they are exactly the same. So at machine precision, they are exactly the same ANC. And we run the calculations. So Filomena worked with Fresco, and she performed the boronate plus nickel 58 breakup calculation that I've shown before. There are no data here because we don't, in this case, we don't care about the experiment. I don't mean to be disrespectful to experimental friends. So the red solid line is what you get with the deep potential and the supersymmetric partner. So the loosely bound, the one without the node is the blue dashed line. If you are colorblind, you don't see a difference because they're on top of each other. So the two curves are exactly identical. You're not sensitive to the short range of the wave function. You're not probing the wave function below 3 Fermi at the best in the best case. We also perform a calculation at higher energy on lead, so it's still Coulomb dominated, and then that's what you get. So a few months ago, I was at a conference and I showed that just to remind my colleagues that you shouldn't extract spectroscopic factors from breakup reactions. But then they said everything here is Coulomb dominated. This is a low energy on a medium mass nucleus, so we've seen that this is mostly Coulomb dominated in the previous calculation. This is on lead, it's a heavy target, everything is Coulomb dominated. Doesn't work. Okay. So you need to test that on nuclear reaction, a nuclear dominated reaction. That's a result for the light nucleus, beryllium-11, impinging on carbon-12. And once again, there is no difference. So there is no way you can infer a spectroscopic factor for Coulomb from breakup measurements. On light target, on heavy target, medium mass target, energy distribution, angular distribution, low energy, high energy, no spectroscopic factor. And I do not want to enter into the observability of spectroscopic factors, even though I don't believe in them. But that's another topic that I will leave for my structure friends. Okay, so when we send the paper to Physical Review C, we had in the abstract, we had the word questionable about the spectroscopic factors, and so that were inferred from measurements. And the referee was not happy, so we changed it. And my first suggestion was to replace questionable by bullshit. And Filomena said, probably that's not the direction that the referee wanted us to go into, okay? So I still think that it's meaningless and to be correct, but we changed it, we adapted it, we changed the wording, and the referee was happy, but it's still what I believe. I don't remember, but we removed questionable, so I don't exactly remember. Oh, but, oh, okay, yeah, that's more, yeah. So and the referee was happy, and it But so the bound state is not the only thing that you probe in these reactions. As we've seen, you also probe the continuum. It's a transition from the bound state to the continuum. So there is, if you're sensitive to the ground state, you're also sensitive to the continuum. It makes sense, okay? It should be, okay? So, and this is the analysis, so the paper I've mentioned with Gérald. So, what we did was this calculation, and we analyzed it partial wave per partial wave. And so the dashed line, so this is also, once again, the breakup cross-section as function of the beryllium-10 neutron relative energy, E, so this one here. And the dashed line is what we get from the output of the calculation. So we saw that, and we said, it came from, that was a few months after my PhD exam, and Ian Thompson from Surrey at the time asked if we could include the D5 resonance, so this resonance here in the spectrum, and we said, yeah, okay, we can, let's try. And Gerald has barely started his PhD, so we tried to find and fit the potential to reproduce what was known about the resonance to the location, which is 1.274 MeV, and the width, which is about 100 or 200 keV. And so this is what we got from the calculation. Holy shit, what is going on here? But when you want to compare to the data, you need to fall with the experimental resolution. There is an energy resolution. What they measure in the experiment is not exactly what you compute. I always complain at the time that we theorists, we had to fold the calculation with the data. Why not unfold the data? But of course, it's not that simple. So I've learned how to do it. And so what we get when we fold it, we have a reduction and we have a width, and we are in excellent agreement with the data. There is a small shift here. I'd like to understand what's going on, but it still means that we can understand, and we can concur with what Fukuda and collaborators published, is that this is a way that you can probe this resonance structure. But this is a resonance structure. It's like a bound state, but in the continuum. What about non-resonance state? And so once again, with Philomena, we started working on trying to understand. That was a bet, actually, because I presented some of the results and said, I don't believe you. And I said, okay, fine, let's do a bet. And she did CDCC calculation. I did my time-dependent method. And so what we did, this is once again the data of the beryllium-11 on lead here in a log scale. I don't know why we did that. It doesn't look good anyway. And so we used the first potential that agrees very well with the data, so we were happy. And then we started using the potential from Fukuda and Al, where they analyzed their data using another potential, which we called V6. We called it V6 because there is a V2, V3, V4, etc. And so we did that, and this is we got a huge bunch of results changing, but it's still bound to the same binding energy, and we see that the shape is good. So there is something going on. What is the influence? What is going on here? And so we started analyzing once again partial wave per partial wave. That's what we did. And this is what we looked. So it's mostly, as I said, P wave transition. So the P half, weirdly, they all agree, but not the P3 half. The P3 half have a different cross section. And the question is why? What's going on here? Well, in the P half, there is a bound state. There is the bound excited state, which is 1/2 minus, and so we reproduce it in the P half. And because you do that, yeah, these are the wave function. This is the wave function of the bound state. They all look alike, same kind of ANC, same binding energy, so everything looks fine. The P half wave function in the continuum, they all produce exactly the same phase shift, but not in the P3 half. So it's the phase shift that you are probing here. The difference that we see here is due to the phase shift. And the phase shift is exactly the same in the P half because there is a bound state, a loosely bound state. And the loosely bound state means that there is a pole in the S matrix at the imaginary energy corresponding to the imaginary momentum corresponding to the bound state. I don't want to into the detail. Just read what Jean-Marc did. So there is an influence of the bound state to the phase shift. So all the phase shifts are identical because we fit the bound state. But there is nothing to fit the P3 half wave so far. And so we have very different phase shift that you can see here, and that affects the continuum. So you need also to pay to take that into account in your calculation. So far, what we've seen is that the breakup is purely peripheral. So it probes only the tail of the wave function. You can get an ANC, but for spectroscopic factor, it's not possible. You will not get spectroscopic factor. What you are sensitive to what we are sensitive to in the calculation is the binding energy of the system. That's number one. That's the most dominant the most significant effect. Then the ANC of the initial bound state, and then the continuum of the projectile. We've seen resonant and non-resonant effects. So resonant effects are strong, non-resonant are much less significant. So you really have that ordering so it's a different magnitude. So first binding energy, second ANC, and then third you have an influence of the continuum. So if only there were a nuclear structure model that could account for that sort of systematic in the expansion. And fortunately, there is one, and it's halo EFT. So this is a work that has been started by Carlos Bertolani, Hans-Werner Hammer, and Mira van Kolk at the beginning of the century. And so what they did is say, so that's a bit similar to what was presented for the nuclear interaction. There is a clear separation of scale. You have a tightly bound core and you have a valence nucleon that is loosely bound. So you have different energy scales. And so you can take that into account in your expansion, and you can build an effective theory on that. And so that was the idea, the original idea, that I have to say, that I have to cite, because otherwise Carlos gets mad at me, and I don't want that. So I cite his paper, and you have heard it. So, but there is a very good review article by Hans Werner and collaborators, a bit more recent, that includes everything that has been done so far. So what is the idea? The idea is that, as usual in an effective theory, you replace a complex system by a contact force, okay? And you go order by expanding that as a contact force plus its derivative. So at leading order, we can't work with contact force in these kind of codes, so we regularize everything using a Gaussian. So we use a Gaussian instead of the contact term. Okay. So at leading order, that's what you have, and there is only one parameter. Okay, the depth of the potential. You fit it in the S wave because that's the leading one, and you fit the binding energy, which is usually known experimentally. Okay, that's the first thing that we need, if you remember the ordering that I've mentioned before. And for all the others, you assume that you don't know anything and you put 0 in the potential. The width of the Gaussian is your regulator, if you want, in that interaction. And in our case, it corresponds to the short range physics that we neglect. So we assume that it goes 1.2, 1.5, and 2. And I won't go into the detail why we start with 1.2 and not 1.0, but we can discuss that later if you are interested. And then there is a next step. You add the second order derivative of your terms. So now you have two terms. You have contact term. You have a central term. You have a surface term. R square appears here, and you start to fit the potential in the S wave and in the P wave. And so in the S wave, you still fit the binding energy. You have two parameters now, V0, V2, and then you need to fit to something else. One thing that you can fit to one thing to which you can fit it is the ANC. And you need a prediction for that. I'll come to that in a minute. So you need an ID for the ANC. In the PIERRE half, there is a bound state, so we can do exactly the same thing, reproduce the binding energy, and then the ANC. We still need a prediction. I'll come to that in the next slide. What do we put in the P3 half? There is nothing at low energy in the P3 half. There is no bound state. There is a resonance, but it's at 2 point something MeV. So that's far enough in the continuum not to worry. So we need some prediction for the phase shift, as we've seen before. I'll come to that in a minute. For the other partial wave, you put 0. And for the rest, it's the same thing. Yep. The chiral would be interesting at the nucleon level, but here you are at much higher. So if you probably know that figure of, I think it's Vitek Nazarevich, where he starts from quarks. Well, it's on top. So you have QCD, where you have quarks. when you have quarks. You go down chiral effect EFT, then you have nucleons and pions. Well, if you don't put the pions, if you are in pionless EFT, okay, fine. So the next step, you have these ab initio calculation of the of the nuclei, where you assume that it's an A-body system. So you have A nucleons interacting with each other. You do not make any approximation. Next step, you go to collective models. So that's density functional theory, for example. There you don't consider really nucleons and all the nucleons. You have a mean field. It's the thing is and it's not a realistic nuclear interaction. You use Gumpforce, which is contact interactions, to simplify the calculations. And then you can go a step further, and then you go back to 1970. Well, 1975 is the date of their Nobel Prize, but to Bohr and Mottelson, where you have collective deformation. So you take that into account and you have a collective model of the nucleus. And it's exactly that kind of idea. So in the collective model of the nucleus, which is basically what we do here, it's, so I'll come to in a minute in the question of deformation, but it's at that level. You have a big blob. You don't go into the detail. There is no reason why you should include the chiral symmetries, because you're way down in the scale. You are way below in the excitation. So this is the chiral part of the interaction. That's here, and we're not. That's the dust. That's what part of the chiral EFT is actually the first part of the dust that we put under the rug. Okay, so we don't want to discuss that. So that's the reason why we don't use that. It looks so simple, actually. So we need predictions. Fine, very good. So Antonio Calci and collaborators, so that's the group of Navratil at Triumph and Robert Roth in Darmstadt. They did a no-core shell model calculation with continuum. So that's no-core shell model with the continuum. So no-core, well, shell model, I think you know what that means. No-core means that there is no core, so it's an A-body calculation. And with continuum means that they account for the loosely bound nature of barium-11. So it's a very complicated calculation, and this is one of the results of that paper. This is the experimental spectrum with this famous shell inversion that I've mentioned before, and they use different interactions. So just nucleon-nucleon interaction. You do not reproduce the shell inversion. You add 3-body force with different kind of regulators, and you see you have a small influence. And then what they did in the end is use this N2LO SAT interaction. So that's a chiral EFT nucleon-nucleon interaction, which is fitted not only to nucleon-nucleon interaction and three nucleon nuclei, but also heavier systems. So they include part of the many-body part in the interaction. And finally, when they increase, this is the conversion, the number of orbitals that they include in the calculation, number of levels in the expansion. They finally get this shell inversion. Okay, so they can manage that. So they have a rather reliable prediction. This is probably one of the most advanced calculation of beryllium-11 that exists so far. And so they predict the binding energy is fine for the 2 nuclei. Well, they tweaked a little bit to reproduce that correctly. Won't go into the detail, but they predict spectroscopic factors, and they predict ANC. They predict spectroscopic factor, and they predict ANCs. And they also predict phase shift. So in particular in the P3 half, they assume that they predict that the phase shift at low energy is 0. So if it's 0, we put 0 for the potential. Okay, so we reproduce that. And so we put that together. We said, okay, we do that, and we perform the calculation. So at leading order, that's what we get. Different ANC. We don't fit the ANC, but they all reproduce the same binding energy. And this is the result that we get for the cross section. So we get the right shape, which is already something, but their magnitude is not correct. So something is missing here. And what we found with Hans Werner Hammer and Daniel Phillips is that this scales as the square of the ANC. So somehow you can infer an ANC by scaling your calculation to the data, and you're not sensitive. You're scaling to the ANC, so you're sensitive to what's going on beyond 5 Fermi. You're not sensitive to what's going on here. So this confirms in another way that the reaction is purely peripheral. You're not sensitive to the short range part of the wave function because the ordering is exactly the ordering of the square of the ANC. And so we fitted the ANC to the value predicted by the structure guys. So once again, we get different interior, but now this time not only the right decay of the wave function, but also the right asymptotics, the right normalization. The phase shifts are predicted to be very similar. That's because there is this loosely bound. I don't want to go into the detail. We get basically the same thing for the PIERRE, so I won't go into the detail. We reran the calculation, and that's what we got. So we are in excellent agreement with the data. Okay, first there is no sensitivity to the wave function, so no sensitivity to the short range part of the wave function. You probe only the asymptotics, you get the same phase shift, so everything's fine. We get exactly the same cross section. There is no sensitivity to that. And with Laura Moschini, we also performed the calculation at the GSI energy, so 520 MeV per nucleon, where you need to put relativistic corrections, and we also get a very good agreement with the data. So what this means is that there is no fitting parameter. We don't touch anything. This is really the output of the calculation, folded with the energy resolution, to be fair, but we have no control over that. And so this confirms the ANC and the phase shift that are predicted by the ab initio people, because we get the right agreement with the data. We looked also at using the same description, we looked at the nuclear breakup of beryllium-11 on carbon-12. And so we got the right magnitude of the cross-section, but something is missing. And that's because the resonance is in the D wave. So we missed something, and this bump also. And it's the same with the GSI data. It's less accurate than the RIKEN data. So you see a bump, but the bump is a bit crude in that case. And so you need to better constrain the continuum. So that's what we did. We went beyond next to leading order. So we added by hand the phase shift at the experimental and width energy, and so the experimental energy and the width predicted by experiment. And we also confirmed that we are in good agreement with the phase shift that is predicted by Calci and collaborators, up to about 2 MeV. And this is what we get. So you see here this huge peak due to the presence of the resonance. There is also a peak in the D3 half. Now, when you fold that with the experimental resolution, this is what you get. So something is missing. We missed something. And so what you need to look at the first degree of freedom that you do not include in the model. And the first degree of freedom that we do not include is the excitation of the beryllium-10 to its 2+. So we published it, we were happy, and then we looked a bit around, and we saw that Antonio Moro and Jose Antonio Lai from Sevilla have shown that there was a significant influence of the 2+. So we need to include it. We're in effective field theory, so you include this kind of thing. This was the idea by Dan Phillips. You include it by a 3-body force. So the process is the following. So you have, that's your target, that's the core, they exchange something, so the core gets excited in the 2+, and it de-excites through its interaction with the neutron. So this is the carbon target, this is the core, and this is the neutron. And so what happens is you have exactly as what you did for the three body force in the nucleon sector. So when you excite to the delta resonance, you replace that by a three body force, and that's exactly what we did. And so when you do that, you also have to tweak the range of the three body force. But when you take the range of the three body force to be the range of the Coulomb target interaction, 3.5, you get the green dashed line, and the green dashed line goes through the data. Not at the at this level, showing that there is something more to that. So you need to include that. This is the energy distribution. This is the angular distribution measured by Fukuda and collaborators, and the green dashed line also agrees very well with the data. So we didn't fit much. It's just the strength of the three body force fitted to this, but we also get the right energy angular distribution using this. So this shows that we now better understand what's going on in the breakup, and that taking the input from ab initio calculation, you can confirm that this is very strong. This is a way that you can confirm ab initio calculation through experiment. Now, you're probably going to say, okay, this is very well. You work in breakup, but there has been transfer calculation, there has been knockout calculation. How do this work in transfer and knockout? So we did that. So it's former PhD student, so Jiecheng Yang, now back in China. And so he performed calculation for the transfer. This is the Schmidt data that I have mentioned before with you. So it's that reaction performed at different energies. So from 20 MeV energy of the deuterium down to 12 MeV, and he has analyzed the dynamics of the, not the dynamics of the reaction, but the sensitivity to the structure of the nucleus. And what we see is that taking that into account with a spectroscopic factor equals to 1, so there is no spectroscopic factor here, but we reproduce, we have the beryllium-11 ANC in agreement with the calculation of Calci and collaborators. We also reproduce the data at all energies. So this is a very good, a very nice achievement. I had another PhD student, Chloe Bourne, now at MSU, and she looked at the knockout cross section, so the one measured by Tom Aumann and collaborators in 2000. So this is the core parallel distribution. She performed the whole calculation using the same next to leading order description of the nucleus, and all the calculations are in good agreement with the data. Here, the difference between the different curves is not the difference between the core neutron interaction, but it's the sensitivity to the nuclear interaction, the projectile target nuclear interaction. And so it's something we know you are sensitive to the to that interaction, so you need to take that into account. But just having the ANC correctly placed, we go through the data without any problem. So the same description can describe Coulomb breakup at intermediate and high energy, nuclear breakup, energy distribution, angular distribution, transfer cross-section, and knockout data. So there is nothing you can do. And this also means that you cannot infer spectroscopic factor from knockout data. And I'm very glad that Jeff Tostervin is not in the room, but that's another debate. Okay, so I come to an end. So the nuclear reactions are used to infrastructure information about halo nuclei. I've just discussed that, not the application to nuclear astrophysics. This will be for another time. We've seen yesterday the different models that can be used. We've seen that they are coherent with each other, but you need to know what's the domain of validity of your model. So when you pick one, just need to know what you're sensitive, what you're doing. There are significant reaction dynamics, so that's one of the way to choose to pick one of the models that you take, and the reaction, and you need to know to what your reaction is sensitive. So it's mostly for the breakup, it's mostly the binding energy. The ANC plays a significant role, not the spectroscopic factor. no way to extract a spectroscopic factor from these data. You have a sensitivity to resonant and non-resonant continuum. And so this is a nice way to probe predictions from ab initio calculation. The next step that we will take is now to use these Bayesian methods to try to know, to try not, because we can't ask ab initio people to do calculation for carbon-19, neon 31 or something like that. It's too heavy for them. So one of the way that something we'd like to develop is a way where we can use Bayesian techniques to try to infer these values directly from the data. And with that, I stop. If you have questions, I'm happy to answer them. Otherwise, just enjoy the sun. And thank you for your attention, and good flight back to home. There is another question. Yep. Oh, yeah. So the reason is the reason is that if you look, so you start from, you start from a bound state. And so your bound state has some behavior which is a peak, and then you decay because it's a halo structure. It decays slowly. Okay. The non-resonant continuum will have a behavior. The non-resonant continuum will have a behavior like that. Okay. There is some distortion in the, so this is non-resonant continuum. Okay. And because, and this is the bound state. Now, and so what you see is that what we've seen is that you have a phase shift here, and you're sensitive to that because it depends where some of the maxima will be, and so it becomes larger or smaller depending on the value of the phase shift. Now, what happens when you have a resonance state is that the resonance state, as you said, it's when they stick together, they stay a little bit more. And so that translates in the radial wave function as something with a huge peak, and then you're back to something that oscillates like this. Okay. So, and if you think that your cross section will be somehow proportional to the square of the matrix element of your, I should write, this is a resonance. So to the final state, and then you have an operator here which explains that transition, and you have your initial state. Okay, square. These two have a large overlap. And so the fact that they have a large overlap means that this matrix element, depending on the value of theta, of this operator, but this will be rather large. So it will be it will be large for resonance, and it will remain small for non-resonant continuum. Okay, so that's why you have that sensitivity, and actually that's why we have So that's why we have this. That's why we have this small sensitivity here, because you are at the resonance, and that's the only place. If you look, that's the only place where you are sensitive to the short range physics. Okay, and it's because the wave function are very different here, and that's exactly where your resonance will be, where the resonant wave function will be. And so that's where you will see a difference between the supersymmetric, the deep potential and its supersymmetric partner, and that's exactly what we see here. So I've not discussed that more, but there you are sensitive to short range physics. Okay. Yeah. Yep. Yeah. Yeah. Mm-hmm. Yeah. Yeah. Mm-hmm. Yeah. No, it's 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 uh it's an annoying question, and therefore it means it's good. Um, it's yeah, it's exactly one of the problems. So you what I want to emphasize here is you need to know what you're sensitive. Um, and for beryllium-11, the good thing is we have a huge amount of reaction data. We have the right reaction tools, so that's what we see because we can reproduce everything. And there is this microscopic calculation. Of course, now you take away the microscopic calculation and then you're naked. The only thing that you have is um, you have the binding energy because it's known experimentally. But let's say you now you analyze carbon 19, there the binding energy is not known very perfectly experimentally. You go to neon 31, you don't even know in which partial wave you sit. So what do you do? And that's where this idea of having these Bayesian techniques, so trying to starting from this halo EFT, so you put the constant and you vary, you let the constant vary with a prior. So you take an assumption there is a prior distribution, so a statistical distribution of these depth V0 and V1, V0 and V2. You let them vary, and then you see what's the influence on your calculation. And then you know that thanks to this very systematic expansion of Halo EFT, you add more and more terms, and you see how this affects your calculation and how you can infer that. But the the problem of Bayesian method is you need to do 100,000 calculations. Okay, one this kind of calculation um, takes about a day. So 100,000 days. Okay, even if you work on 100 computers, it still means a lot of time. So that's what we've a bit discussed that yesterday with Jérôme Margueron. Then you can use an emulator. You could use simpler reaction models to try to have an idea and then see what's going on. So that's the goal. The problem remains that you are sensitive to a lot of things, so you can't just say, okay, I will extract a spectroscopic factor because you are sensitive to other things. So that's the important message. Yeah. Yeah. Mm-hmm. Yep. Yeah, yeah. Hmm. Yeah, yeah. Hmm. Yeah. Hmm. Yeah, yeah, yeah. So recently we had, so I have a PhD student now who's trying to include a core excitation using this kind of EFT approach. So you include explicitly, instead of using just the 384s, you include explicitly in the model. So that makes more complicated. The comment of Hans Feldmayer at the time, a few months ago, was just one excited state of the core will not help you. You need to include a huge amount of information. So that's, yeah, that's a question. We can wonder what's going on and what needs to be included. Yeah. But there was another question. Yeah. Everything is in the poster form, posterior. Yeah. 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 No. So it's really um it's really saying, okay, something else happens, we don't know what. And so you could, I think at one point maybe some people started to analyze exactly the shape, if you have a surface term, if you have a central, just a central term is sufficient. Try to understand what was going on, but I think it remains just it's just, that something else happens. I've never really worked in this analysis of optical potential. That was a huge theme of research in the 70s, 80s, and maybe up to 90s, trying to understand what was going on, but I don't think it went anywhere. Yes, you can include them explicitly. Okay, but that's challenging. So having, for example, you could imagine a model of the reaction that includes the breakup channel and then the transfer channel. So the Jacobi set of coordinate that we use is the projectile, the target projectile, and then within that you have so it's the what we call the T. It's the T. But that's a Jacobi set of coordinates, but it's not the ideal one to describe the transfer, because in the transfer the fragment will be absorbed by the target and the core moves away, and that's one of the what we call the Y Jacobi set of coordinates better described. So what you should do is have a description of the reaction that includes all the three Jacobi sets of coordinates. That exists. It's the Fadeev equations, but that adds another layer of complexity. So you have people working on that. Arnas del Tuva, for example, Antonio Fonseca, have worked on that, and so you have that kind of possibility, but so far it's limited because they have a problem to deal with Coulomb. So deuterium-induced reaction is fine. If you go to heavier target, then it starts to be a problem. So that's one of the issue. Okay. Yeah. Mm-hmm. No, you cannot because the collision time is much smaller. So when you have a compound nucleus formation, it has to stick together to a long time, and you should completely forget the way you were formed. So the nucleus should somehow forget the incoming channel. That's not the case in a resonance, because if I mentioned this resonance, for example, you will not change partial wave. So the two come close together, they stick a little bit together, but then they decay exactly in that channel, and you will not have something that is fully isotropic, independent on the uh, incoming direction. For example, if you see that then coming, so it's not it's not the same thing. The compound nucleus formation is really you it's there is a clear separation of scales, but on the time scale, so it's really you form a compound system that stick together and then eventually decays, but with complete absence of memory of the incoming channel, which is not the case here. So this is still collision time, so 10 to the minus 20 minus 19 seconds. Compound nucleus formation is much longer. So you have people doing these kind of compound nucleus calculation using a time-dependent Hartree-Fock calculation. So ask your neighbor. She's not an expert in that, but she knows someone who is, and so where it's there you it's a mean field calculation, but you see the two nuclei approaching together as mean field with the time evolution, and then forming one mean field, and then evolving after that. So it's a different topic. Mm-hmm. Yeah, A+1, yeah. Yes, in this case, but it once again it will depend on actually how the resonance looks like. And so in particular, if we look at this case, here, for example, we use exactly the same description for the 3/2 plus and the 5/2 plus resonances. And it works very well for the 5/2 plus, but not that much for the 3/2 plus. But actually what happens is that at 3 MeV, there is a threshold where the core, exactly as what Enrico mentioned, the core gets excited in its 2 plus. And so what it seems is that resonance state is more similar to the core, the structure. This one is probably more like a barium-10 in the 0 plus 1 neutron in the D5/2, but this one is most likely has a strong component with the core in the 2 plus, plus one additional valence. And that's why we have problem with our simple model to describe that resonance, because that channel is not explicitly included. This is virtual excitation of the core. So the core gets excited in 2 plus and then de-excites by interacting with the neutron. Here, that is not sufficient to explain that, and it's probably more like there is an actual excitation of the core. The core gets excited in the 2 plus and exits the reaction in the 2 plus. So this is more, so you have a link, but that depends on the structure of the resonance. Okay. So I think we are all exhausted. Nothing. So to me, there is spectroscopic factors are not observable, period. You get it from your structure calculation, but then you change the interaction by unitary transformation, and you change the spectroscopic factor, not changing the ANC. So it's okay. On these very unwise sayings, I wish you we still have lunch, I guess, together, and then a nice weekend, safe trip back, and safe journey in the physics